In this video, we are going to solve a very common example of conductive heat transfer with resistances in series. And this is in a cylindrical system. In particular, this is a system wherein a pipe is involved. Let's take a look at the problem. Saturated steam at 40 psi flows at 5 feet per second through a Schedule 40, 1.5-inch steel pipe. The conductive heat transfer coefficient by condensing steam on the inside surface may be taken as 1,500 BTU per hour per square feet per degree Fahrenheit. The surrounding air is at 80 degrees Fahrenheit with an outside convective coefficient of 3 BTU per hour per square feet per degree Fahrenheit. We are to determine three things. First, for letter A, I want to determine the rate of heat loss per 10 feet of that bare pipe. And as a bonus, I've given here the thermal conductivity of the pipe. It's around 16 watts per meter per Kelvin. For letter B, we are going to determine the rate of heat loss per 10 feet of bare pipe, but it's now insulated with 0.5-inch thick rubber. So we're going to take a look at what's the effect of adding an insulating layer to the rate of heat loss of the pipe. I've also given here the thermal conductivity of rubber. It's 0.2 watts per meter per Kelvin. Now, for the final one, we want to determine the external surface temperature of the bare and insulated pipes because we want to see what's the difference between a pipe that's bare and a pipe with added insulation. So would that affect the overall external surface temperature of the pipe? Hopefully it will, right? Because the purpose of the insulation is twofold. It's first to reduce the rate of heat loss. And the second one is, of course, to protect ourselves because we might accidentally touch the pipe and we don't want its surface temperature to be that hot. Okay? Now, you can take a look at my notes right here. I've given some very common conversion factors for thermal conductivity and for heat transfer coefficient between English units and SI units for our reference as we solve this problem. Okay, let's begin. For the first one, we are considering a bare pipe. So take a look at my illustration here. This is the cross section of the pipe, and at the inside cavity here, we have steam, right? And then at the outside, we have air. And your saturated steam is at 40 psi or pounds per square inch. Now, you can take a look at any thermodynamic diagram or thermodynamic table for water to determine what's the equivalent temperature of steam at this saturation pressure. I have gotten that for you. The saturation temperature of steam at that pressure is around 403 Kelvin. 403.57 Kelvin to be exact. In degrees Celsius, that is 130.42 degrees Celsius. So this is the temperature of the steam inside that we're going to use for our calculations. Now, the temperature of the air was mentioned to be 80 degrees Fahrenheit. Now, just to be consistent, let me convert this to degrees Celsius. That will be 80 minus 32 divided by 1.8. Sorry. So that is roughly 26.67 degrees Celsius. I'm converting everything to SI units for our convenience later on when we solve the problem. Now, one very important thing to know here is the direction of heat transfer. Remember that thermodynamics tells us that heat is always spontaneously transferred from high temperature to low temperature. So, if the temperature inside of your pipe is 130 degrees Celsius roughly, and the temperature outside of the pipe, that for air, is 26.67 degrees Celsius, so thermodynamics tells us that the transfer will be from the inside of the pipe to the outside of the pipe. Let me illustrate that. And the transfer will be on the radial direction. So I'm going to designate this as capital Q sub R. That's the rate of heat transfer on the radial direction. Okay? It's from high temperature inside to low temperature outside. Now take a look at the path that your heat is going through. It starts with going through the steam inside of the pipe, and then it goes through the pipe material itself, which is steel, and then lastly it goes through air. So we have two modes of heat transfer happening here. We have convective heat transfer happening inside in the steam compartment. We also have convective heat transfer happening outside in the air Presumably, this is natural convection. And then we have conductive heat transfer happening once you are in the material of the pipe itself, right? So there's three resistances to be encountered, and they are to be encountered in series. Because if you take a look at my green arrow here, it starts at the inside of the pipe and ends up at the outside of the pipe. You are going through the three different resistances this way. This resistance is due to convection inside. This resistance is due to conduction in the pipe material. And the last resistance is due to convection on the outside of the pipe. This is the basis of our equivalent resistance diagram. If I draw it this way, you can clearly see that with the specified direction of our heat transfer, we are going through it in series. This point right here is the temperature of the steam inside. And this point right here is the temperature of the air outside. This is the direction of the radial heat transfer. It's from left to right in my drawing here, from steam to air. And it's going through the resistances in series or one at a time. I'm going to call this R1, R2, and R3 for us to better be aware of what are the resistance being encountered. The first resistance, as mentioned earlier, is due to convection. And the resistance due to convection is simply 1 over H times A, wherein H is the convective heat transfer coefficient, A is the perpendicular surface area to the direction of heat transfer. Since we are encountering this at the inside of the pipe, I'm going to label this as H sub I, A sub I, meaning it's for the inside surface of the pipe. Now, the partner of this is the third resistance, which is still convective heat transfer at the outside. So it's still the same resistance, 1 over HA, but we have to specify that this is for the outside area of the pipe because it's important to take note that for cylindrical systems like this, the inside surface area is not the same as the outside surface area. The diameter changes, right? And if the diameter of the cylinder changes, then its surface area would also change. We have here the formula for surface area of a cylindrical shell that will be pi dl. So if it is for the inner surface area, that is pi dil, wherein di is the internal surface area. And if it is for the external surface area, that is pi dol. Now, where are those diameters? Let us point that out here. If you measure from the center of the pipe up to this point right here, this is my d sub I, or the inner diameter of the pipe. And similarly, if you measure it up to the outer surface, that would be d sub O, or the outer diameter of the pipe. Where do we get those values? Now, it was mentioned in the problem that your pipe is 1.5 inch, schedule 40. Take note that the 1.5 inch here is called a nominal diameter. That's not really the actual diameter of the pipe. Now, you might want to consult a table of steel pipe properties in order to determine what are the actual internal and external diameters for a nominal diameter given a schedule number. And the schedule number is just an indication of how thick the wall of the pipe is. So, for a 1.5 inch steel pipe, schedule 40, we have the inside and outside diameters given as follows. The internal diameter is 1.61 inches. By the way, I'm getting all of my values from the 9th edition of Perry's Chemical Engineer's Handbook. So if you have other sources, you may use that as well. Now, inside diameter, 1.61 inches. Outside diameter is 1.9 inches. These are what we're going to use for the surface areas mentioned earlier. So at this point, we have already characterized the resistance encountered due to convection on the inside of the pipe and the resistance due to convection on the outside of the pipe. Now, the heat transfer coefficients HI and HO were already given in the problem. That is 1,500 BTU per hour per square feet per degree Fahrenheit on the inside, and it's 3 on the outside. Now, if you are comfortable with dealing with parameters in SI units, then we just have to convert it from English units to SI units. I have the conversions right here. Now, there's only one thing missing in our equivalent resistance diagram, and that is the second resistance. Now, remember that the second resistance encountered here, so let me label it in here. This is R1, R2, and R3. The second resistance is due to conduction in the steel pipe itself, right? Now, in some cases, you might argue that the resistance due to conduction is negligibly small if we compare it to the resistance encountered due to convection on the outside air. But for the thoroughness of our solution, let's include the resistance due to conduction. For a cylindrical shell, the resistance due to conduction is calculated as the natural logarithm of the ratio of the diameters, outer over inner diameter, that is dO over di. You can also use radius because it's a ratio, it doesn't matter, divided by 2 pi KL, wherein K is the thermal conductivity of the material, in this case that's for the pipe, and L is the length of the system. We are given the length of the system, that is 10 feet of the bare pipe. We now have here R1, R2, and R3. Now, how do we characterize the rate of heat transfer? The rate of heat transfer, the radial rate of heat transfer, always remember, is simply the driving force divided by the resistance. This is a very powerful expression of this rate equation that we can apply this into anything involving heat transfer, right? So in our equivalent resistance diagram, if you are to apply this equation, you just have to pinpoint two different ends and apply this equation. So for example, if we are going to consider the entire system, you might want to consider this as your starting point, steam inside, and this as your ending point, air outside of the pipe. The driving force is simply the temperature difference between those two identified points. That's simply temperature of the steam minus temperature of the air. That's your driving force, right? The driving force is what makes heat transfer possible, the difference in temperature between 2 points. Now, for the resistance term, since your resistances are in series, you can simply add them together. So if these are my two identified points, the total resistance is simply R1 plus R2 plus R3. That's the beauty of having resistances in series, because the resistances are additive. So if I'm going to consider these two terminal points, I can write my equation for rate of heat transfer as driving force is temperature of steam minus temperature of air divided by the total resistance encountered, R1 plus R2 plus R3. And then that's it. All we need to do now is to calculate everything so that we can determine the rate of heat loss for 10 feet of bare pipe. Now, for simplicity, let me show you how I calculate the individual resistances, and then later we can add them all up and then come up with the rate of heat transfer. So let's have here values of R1, R2, and R3. If you're already comfortable at this point in substituting this directly into your calculator, feel free to do so. But in some calculators, it might not fit if you do it all at the same time here. So let's calculate for the resistances individually. Let me do that in my calculator here. So let's start with R1. The first resistance, that's resistance due to convection on the inside. That is 1 over HI. Now, the given heat transfer coefficient is 1,500, but it's in English units. Take a look at the note here. You can convert from English units to standard SI units by multiplying this with 5.678. So according to this note right here, the equivalency is that 1 BTU per hour per square feet per Rankine is equivalent to 5.678 watts per square meter per Kelvin. So this is a very fast way for us to be able to convert heat transfer coefficients. Take a look at the other note there. That's for thermal conductivity, and that I don't think we're going to use this for this problem because the thermal conductivity is already given in standard SI units, but that's just for your reference. Okay? Do not confuse yourselves between the thermal conductivity and the heat transfer coefficient. Take a look at the units. The difference is subtle, but for heat transfer coefficient, your denominator is in square feet or square meter for standard SI. For thermal conductivity, it's in meter only or feet for English. That's the difference between those two parameters. Okay, going back to the first resistance, that is 1 over H sub I. I'm right here already for my calculation, right? And we multiply this by the internal surface area of the pipe. Take a look at this equation. That's pi, di, and L. Make sure to convert everything to standard SI. So we multiply this with pi. And then the internal diameter is 1.61 inches. Multiply that by 0.0254 to make it meters. And multiply that with the length of the pipe, that is 10 feet. Multiply this by a conversion factor to convert it to meters. So from feet to meters, multiply it by 381 over 1250. You can use whatever conversion factors you are aware of in converting these values. Okay? Take a look at my calculator. It's showing 2 points. It's around 3 times 10 raised to negative 4. The unit of resistance is always Kelvin per watts if you are using standard SI units. Okay? Kelvin per watts. That's temperature over power. And then we do the same for R2 and R3. So let me do the calculation for R3 first, since we are on the topic of convective resistance. So that's 1 over HO, or the external heat transfer coefficient. That's 3 BTU per hour per square feet per degree Fahrenheit. You multiply it by our conversion factor right here, 5.678, times the external surface area right here. That's pi times the external diameter, 1.9 inches. Convert this to meters, times length. Convert feet to meters. Do not forget to convert your units. The resistance for the third one is 0.127. Let's just do 0.127. This is Kelvin per watts. Now, I want you to take a look at the relative values of the first and third resistances. The first one is very, very small. That's the resistance due to convection inside. The third one is large compared to the first one, right? Because this is only due to natural convection on the outside, and the rate of heat transfer due to forced convection is much faster due to the rate of heat transfer due to natural convection. Okay, that's why the resistance is greater for natural convection. It's lower for forced convection. Now, let's calculate for the second resistance. This is the one with the different formula right here. That is the natural logarithm of the ratio of diameters, external diameter over internal diameter. Now, notice that I did not convert from inches to meters. That's because it's a ratio, right? It doesn't matter. But if you want to make sure, just convert it to meters. Our denominator here is 2 pi KL. That is times pi times the thermal conductivity of the pipe. It's already in SI units, right? It's 16 watts per meter per Kelvin, times the length of the pipe. 10 feet, again, do not forget to convert to meters. This is my resistance for the, this is my conductive resistance for the pipe. 5.4 times 10 to the minus 4 Kelvin per watts. Now, take a look at the value of R1 and R2 compared to R3. We can say here that R1 and R2 are very small in comparison with the third resistance, R3. So, the convective resistance outside of the pipe, it actually controls the rate of heat transfer, right? Because it's always the largest resistance that controls the rate of heat transfer. Now we are ready to calculate the rate of heat transfer. Simply follow this formula right here. Temperature of the steam is 130.42 degrees Celsius minus the temperature of air outside, 26.67 degrees Celsius. Now take note that if you subtract temperatures in degrees Celsius, that's the same as subtracting temperatures in Kelvin, right? And we divide that by the sum of the resistances. So let me add all of the resistances. The last one is 0.127. This is our rate of heat transfer. That is 800. Let's make sure that these are correct. Okay, that's 812. Let's just round it off at 812 watts. Be very careful with your units. So my unit in the numerator rather is kelvins or degrees Celsius, and then the remaining unit in the denominator is Kelvin per watts. So that's Kelvin over Kelvin per watt. That results to a unit of watts. So in order for us to have some flexibility, let's try to convert this to BTU per hour. So if you want this in BTU per hour, you simply divide by 1055 and multiply by 3600. This is 2769 BTU per hour. So these are two different values, two different numerical values, but they're representing the same rate of heat transfer, right? It's just with different units. And that's it. We have already determined the rate of heat loss for 10 feet of the bare pipe. Now for letter B, we are being asked to calculate the rate of heat transfer once we have applied a layer of resistance. That layer of resistance or added resistance is an insulator. We applied a 0.5-inch thick rubber. We wrapped it around the pipe, and if you take a look at the new cross section, this is how it should look like. So the white layers, that's the original pipe, the original steel pipe, and the green one is now your added 0.5-inch thick rubber. Now, please do notice that we have introduced a new diameter or a new radius in this case. So if you go back to our illustration before, this first one right here, if we are to complete it, this is my inner diameter, or that's the inner diameter of the pipe. And I know that I'm just drawing the radius, but you can understand that it's for the entire diameter, right? The second one right here is the outer diameter of the pipe. We used DO for that, but then we have introduced a third diameter right here. This is the overall external diameter of the pipe once we have applied the rubber. And as you can understand, your total external diameter should be larger than the external diameter of the pipe. I'm going to call this DE to signify the external diameter. How do we calculate that value? Now, this is arguably where most people would have it wrong, because you might be tempted to simply add 0.5 inches to the existing external diameter of the pipe. So let me carry over those values. The internal diameter of the pipe itself is 1.61 inches. The external diameter of the pipe is 1.9 inches. You cannot simply add 0.5 inches to 1.9 inches and call that your external diameter. Because remember that if you're considering diameters, you should add 2 times of the thickness of your added material. So I'm going to say that the external diameter will become DO plus twice the thickness of the rubber layer. That's my delta R. So the 0.5 inch is my delta R. That's the thickness of the added insulation. Okay? Now this becomes 1.9 inch plus 2 times 0.5 is 1. So this becomes 2.9 inches. That is our overall external diameter. Now, it's still the same system. So inside you still have your steam inside of the pipe, and then outside of the system is still air. Still the same temperatures from before. So let us carry over those temperatures. Temperature of the steam is 130.42 degrees Celsius. And the temperature of the air outside is 26.67 degrees Celsius. So, since those are still the same temperatures, we expect the direction of heat transfer to be the same. It starts from the high temperature and ends up with the low temperature. This is my Q sub R. It's the radial. The heat is being transferred in the radial direction. Now, notice that we have added a layer. We have also added another resistance. This is the first resistance as usual. It's resistance due to convection inside. The second resistance is due to conduction in the pipe. Third one is resistance due to conduction in the rubber layer. And the last one is due to convection on the outside. All in all, the change in our diagram would just be an addition of a fourth layer. This point right here would still be the temperature of the steam. This point right here, temperature of the air. The first resistance is R1, and so on. The first resistance is still due to convection inside, that is 1 over HIAI. Now, this R1 right here is the same numerically as our R1 from before because it's the same parameters, right? It's the same value of HI. It's the same internal surface area. Now, for the second resistance right here, it's still the same. It's the conductive resistance in the pipe itself. It's ln dO over di over 2 pi k of the pipe times L. So R1 and R2 can just be carried over from the first item, right? We can carry over their values. They're exactly the same. Let me copy the values. So it's 3 and 5.4. Kelvin per watts. And then after that, we just have R3 and R4. But you have to be very careful because remember that R4 here, the fourth resistance, is resistance due to convection on the outside. We can write it as 1 over HO. This is the external heat transfer coefficient, but your area should be the overall external surface area of the system. And this should not be AO. It should be AE, or the external surface area. Because when you place that rubber layer on your pipe, your overall external diameter is now DE and not DO. So, the last resistance here, R4, is not the same as our last resistance here. You have to take note of that, right? Because your overall external diameter is now different. I'm going to take note here that AE is now pi DE times L, or the length of the pipe. Okay? Make sure that you understand that the overall external diameter is different, so we cannot carry over the previous value. How about R3? What is the resistance due to conduction in the rubber layer? It still follows the same formula, natural logarithm of the ratio of diameters, but take a look at the thickness of the rubber. The external diameter is DE. The internal diameter of the rubber layer is DO, not DI, because we're only talking about the rubber layer. DE over DO divided by 2 pi KL, but now the K here, or the thermal conductivity here, is for the rubber. So R2 and R3 are expected to have different values because they have different thermal conductivities. The steel pipe is much more conductive compared to the rubber pipe. The conductivity of the rubber is only 0.2 watts per meter per Kelvin, right? It's an insulator. It's supposed to arrest or to slow down the transfer of heat. So same as before, let me calculate for R3 and R4. Let's start with R3. That is natural logarithm of the ratio of the diameters, 2.9 inches divided by 1.9 inches, divided by 2 pi times K of rubber, 0.2, times the length of the pipe, 10 feet. Don't forget to convert to meters. This is my resistance due to conduction of the rubber layer. 0.11, let's use 0.110 Kelvin per watts. Let's calculate R4, or the last resistance. That is 1 over HO, that's 3 BTU per hour per square feet per degree Fahrenheit. Use the conversion factor here to convert it to SI units. Multiply by 5.678. And then take note of the external surface area, that is pi times dE, 2.9 inches. Convert that to meters, multiplied by the length, 10 feet. Again, convert to meters. I'm getting 0.0832 Kelvin per watts. Notice that this is not the same as our convective resistance earlier for the external, right? Because again, the surface area changed. But what hasn't changed is how we calculate for the rate of heat transfer, Q sub R, that is still driving force over resistance. Now, there was a bit of change in our diagram because we added another resistance, but I'm still looking at end to end. The first one is temperature of the steam. The last point is the temperature of air. So in terms of temperature difference, that is still temperature of steam minus temperature of air divided by all of the resistances that we passed through from steam to air. That is R1 plus R2 plus R3 plus R4. Or the summation of the resistances. That's the beauty of resistances in series. You can simply add the resistances. Now let's substitute all of these values in our calculator. Let's take a look at the results. Temperature of steam minus temperature of air divided by the sum of the resistances. Notice again that the first two resistances are very small in comparison to the last two resistances. So in some cases, we might neglect those values, but for thoroughness, let me include all of the resistance values because we already have the values. Might as well just substitute them, right? 0.0832. This is now what I'm getting for the new rate of heat loss. That's 535 watts. And then let's also get that in BTU per hour. So for this to be in BTU per hour, we divide by 1055, multiply by 3600. That's 1825 BTU per hour. We can compare the two values between A and B, right? In the bare pipe, if there is no insulation, you are losing heat at a rate of 812 watts. But once we provided an insulating layer of rubber, the rate of heat loss was reduced to 535 watts. It's not much of a reduction because there are other materials that have even lower thermal conductivities. So say for example, if we use Teflon instead or an insulating cotton layer, then we might be able to further lower the rate of heat loss. Okay? But for this problem, this is the result. So there is a decrease in the rate of heat loss. And that's it. We were able to calculate it already. So there are very subtle changes to our equivalent resistance diagram that we have to take note of. But all in all, with very diligent changes to the external surface area, we were able to recalculate the rate of heat loss. Now let's move on to the last one. For the last item, we are being asked to solve for the external surface temperature of the bare and the insulated pipes. This is where it gets interesting. So let me again draw the equivalent resistance diagram for a bare pipe. So this is for the bare pipe. We only have three resistances, right? This is temperature of steam. This is temperature of air. And we have the three resistances. R1 and R3 are due to convection. R2 is due to conduction. Now, we mentioned earlier that when we calculated the rate of heat transfer in the radial direction, we used temperature of the steam and temperature of air as our guidelines. That's our driving force, right? From T steam to T air. And we included all of the resistances in between. Now, since the resistances are in series, the rate of heat transfer that you're calculating for the overall system is also the same as with every other resistance. That means that the total rate of heat transfer QR is also equal to the rate of heat transfer experienced in the first resistance, that's still equal to the rate of heat transfer in the second resistance. It's still equal to the rate of heat transfer in the third resistance. No matter how you divide this diagram right here, the rate of heat transfer is constant. Let me get that value again. For the bare pipe, Q is 812 watts. So we can use this to our advantage because if we are to calculate the external surface temperature of the bare pipe, we can easily locate that in this equivalent resistance diagram here because the junctions between the resistances are temperature junctions. This point right here is the external surface temperature of the pipe. I'm going to call that TS out for the outer surface temperature. And this point right here is the internal surface temperature of the pipe. But we are not interested in that, right? Because what we are interested in is what we can touch, and that is the external surface of the pipe. So take a look at the green markings here. If I'm going to slice the equivalent resistance diagram from here to here, this one right here should have the same value of the radial heat transfer, rate of heat transfer Q. But our definition of the driving force will change. So if I'm going to write it like this, QR3, which means this is the rate of heat transfer passing through the third resistance, is equal to the driving force in the third resistance, which are marked by the green lines here and here. That becomes TS out minus T air divided by the only resistances that you passed through between these two green lines, and we only passed through R3. And this is equal to 812 watts. This is how we are going to solve the external surface temperature of the pipe. That's the beauty again of resistances in series. The rate of heat transfer is constant all throughout. Okay? Now we can easily solve for this because we already have a value of R3 earlier. Let me fetch that quickly. R3 for letter A is this one, 0.127 Kelvin per watts. If you want to recalculate with the fresh values, you may do so. Okay. Sorry, I lost the value. 0.127 Kelvin per watt. Temperature of the air is 26.67 degrees Celsius. Now we can calculate for TS out, or the external surface temperature of the pipe. Take a look at my calculator. The external surface temperature will be the temperature of the air, 26.67, plus the product of the rate of heat transfer and R3. So that is 812 watts times the resistance 0.127 Kelvin per watt. I'm calculating roughly 130 degrees Celsius. So let's just round that up to a whole number. But you can do 2 decimal places. It's up to you. This is the external surface temperature of the bare pipe, which is just marginally lower than the temperature of the steam. To recap, earlier we used a temperature of steam of 130.42 degrees Celsius. So this tells us that the material of the pipe itself offers very little resistance to the heat transfer, right? Because there's barely any difference between the temperature of the steam and the external surface temperature of the pipe. It's still very hot. It's still very dangerous for us to touch. Now, let's compare that to the same calculations, but now for the insulated pipe. For the insulated pipe, the only difference was that we had 4 resistances, right? This is temperature of the steam. And on the other end here, I have the temperature of the air. Now, what are the junction temperatures here? We now have 3 junction temperatures. Let me drive you back to our illustration earlier. Where are those junction temperatures? Take a look at the points here. Let's use a different color. This one right here, this is the external surface temperature, TS out. right? This one right here is the junction temperature between the pipe and the rubber. Let's just call that T sub J for junction temperature. And this right here is the internal surface temperature of the pipe. If you translate that to the resistance diagram, these are their positions. This is your TS in, or the internal surface temperature. This is the junction temperature between the pipe and the rubber. And this is the new overall external temperature, TS out. Let's transfer that to our new diagram right here. This is TS in. This is TJ. This is TS out. Let's do the same thing that we did earlier. I can slice my equivalent resistance diagram to just starting from here, ending from here. I still can use the same value of Q sub R, or the rate of heat transfer, but we're going to use the value for the insulated pipe. That is from part B. That's the 535 watts that we calculated earlier. So we take notes that QR4, which is the same as Q sub R, is 535 watts. And that's equivalent to the driving force of TS out, if you only take a look at the last resistance here, minus T air, divided by the only resistance that we passed through, which is the fourth resistance in this case, R4. Let's fetch the value of R4 from earlier. That is 0.0832 Kelvin per watts. Now we're ready to solve for the new external surface temperature. Again, that will be the temperature of air, 26.67 degrees Celsius, plus rate of heat transfer, 535 watts, times the resistance, the fourth resistance, 0.0832. I'm getting 71 degrees Celsius. Now, it's a remarkable difference between the external surface temperatures of the bare pipe and of the insulated pipe, right? So let's make sure to label this one. This is for the bare pipe. This is for the insulated pipe. If you touch the external surface of the bare pipe, you will burn yourself for sure, because that's 130 degrees Celsius. That's more than the boiling point of water, the normal boiling point of water. But if we include a rubber insulator, that brings it down to 71 degrees Celsius. It's not that cold. You will still be able to burn yourself if you hold onto it for too long, but at least it's manageable. We were able to drastically bring it down. So what can we do to further decrease the overall external surface temperature? You might want to change your insulator or your material. Instead of using rubber, you might want to use materials with lower values of thermal conductivity K. There are lots of materials like that. But in general, this is how we solve these types of problems. So to recap, in this example, we were able to construct an equivalent resistance diagram for conductive and convective resistances in series. And we were able to calculate the overall external temperatures. And using this method, you can also calculate for the other temperatures involved in this system. Okay, that's it for this problem. Thank you for listening. I'll see you on the next one.